Welcome back to Honors Calculus. In this video, we're going to start a discussion on Lesson 7, Extrema, with the ideas of absolute and relative extrema, titles you can't see behind my head. So let me get my head out of the way and let's just dive right in. We've talked previously about the idea of extrema. Remember, extrema is the catch-all term for a maximum or a minimum. So if you can find a maximum, you've found an extreme value. If you find a minimum, you found one of the extreme values. Extrema is the collection of all of the maximums and minimums of the situation. And then the extreme value theorem tells us that if we have some function f which is continuous on a closed interval from A to B, then f attains its maximum and minimum on that interval. We're going to call the maximum and minimum that f attains on the closed interval from A to B the absolute maximum on AB and we'll call the minimum that the extreme value theorem tells us exists the absolute minimum on AB. And generally speaking, the absolute maximum and the absolute minimum are going to be useful in problem solving. But one of the shortcomings we discussed when I introduced you to the extreme value theorem and the intermediate value theorem and the other theorems that went along with those in our discussion is that the theorem gives us no way of finding the absolute maximum or absolute minimum. So we need a tool that will allow us to get there. And to build that tool, we're going to start with the idea of a relative extrema. Let's take a function f, and we're going to insist that it is continuous near some point C. What does near mean? Well, I'll define that in a moment, but I don't want to give too many intervals in the same definition. But to say that a function is continuous near C, that means that we can find some open interval that contains C where the function is continuous on that open interval. We will say that f of c is a relative maximum of f if and only if there is some open interval ab in the real numbers with c in that open interval, and f of c is the max of f on that interval. And then we can also have a relative minimum, just switching maximum for minimum everywhere in this definition. I'm going to use the marvel of technology and just copy this definition, paste it, and do some quick editing. All right, we don't need the title again. We've already established that we're talking about relative extrema. And again, we're getting rid of the word maximum, which occurs twice, and we are simply replacing it with the word minimum. So the idea here of a relative maximum or a relative minimum is the idea of maximum and minimum that you are introduced to in algebra in discussing the graphs of functions. If you think about a generic polynomials graph, you might see a function that looks, that was horribly ugly. Let's try that again. All right, let's draw some coordinate axes. And to make it stand out, I'll even use a different color. Let's say we have a fourth, maybe fifth degree polynomial. So the graph of the polynomial might look something like that. If you look in an interval somewhere near this point, that point is the maximum in that interval. In fact, that particular point is the maximum everywhere on the graph, but it's the maximum in a region near it, so it's a relative maximum. A little bit more telling might be this point. If we look at an interval near that point, then that is definitely the minimum. But if you look at the graph and you look over here, there are definitely parts of the graph that go well below that point. So it's not the minimum for the entire function, but if you look just in the region near it, it is a minimum in that region. And likewise, the peak right there. This is the maximum of the function if you look at a window somewhere in the general vicinity of here. But if you expand the window out too far, you'll start including these points where the function gets above that point. For a relative maximum or a relative minimum, our goal is to be able to cover up some of the graph and see that in a small window, that point is a maximum or a minimum. In an absolute maximum or an absolute minimum, we don't have that ability to cover things up. All right, let me get my head back out of the way and let's take a look at another picture. All right, here we have a function which has a vertical asymptote in its graph. So if you look at a window somewhere near this vertical asymptote, there is no maximum because the function keeps going upward. There is no minimum because the function keeps going downward. We again have a couple of relative max and min, right? Relative minimum is right about here. Relative maximum somewhere about there. Comparing that with this idea of an absolute maximum or minimum, right? If we are careful and chop the function near but not at the asymptote. Well, in a closed interval, in say this box, we'll call this A, we'll call this x equals B, and talk about the interval from A to B, the absolute minimum is the point way down here. The absolute maximum is also the relative maximum because I cut this so that the relative maximum was still in there. Right, so there's a visual idea of what's going on. When we're talking about finding an absolute maximum or an absolute minimum, one of two things is going to happen. Either the absolute maximum is going to be at one of these relative maximums that I've just introduced you to, or the absolute maximum is going to be on one of the endpoints of the interval. So when we are looking for an absolute maximum or an absolute minimum, our process is going to be to find the relative maximums, relative minimums, find the endpoints, and evaluate at all of those things. We will get there eventually, and we'll start looking at problems. But I want to go through and show you how this is supposed to work, because it's not obvious at first that these relative extrema are actually useful. On top of that, using the tools that we've been talking about recently in the derivative, it turns out that it's relatively simple to find an absolute maximum or an absolute minimum. So that's where we are going next. Let's get a very vague definition or a very vague setup. So let f be any real valued function of one real variable and I'm going to give it a very careful restriction that we have some point called C where the function is defined. We say that this C is a critical value, sometimes called a critical point of f, if and only if f prime at C is equal to 0, or f prime at C is undefined. So if the function is not differentiable at the point in question, we will call it a critical point. If the derivative of the function is 0 at the point in question, we will call it a critical point. And the theorem that I want to introduce you to claims that every extreme value of a function occurs at a critical point, right? Every relative extrema, absolute extrema occur in weird places based on the boundaries of the interval in question, but relative extrema always occur at critical points. Careful with this definition, or with this theorem. Every relative extrema occurs at a critical point. Not every critical point is an extrema. I'm not going to prove this theorem, but I'm going to give you a little bit of evidence to think about why this theorem works. If I draw another arbitrary curve, this one will be a little bit simpler than the one we had before. Something that looks kind of like that. What I want you to notice about this curve is that it definitely has what we would call a relative maximum, and it definitely has what we would call a relative minimum. Thinking about what it means to be a relative maximum or a relative minimum. A relative maximum is a point where the function is increasing and increasing, and then suddenly stops increasing before it starts decreasing again. And a relative minimum is a point where the function is decreasing before it stops decreasing and then starts increasing again. Whether the function is increasing or decreasing, that's the rate of change of the function, the derivative of the function. And so we have a derivative that is positive, and then it is negative. And there are only two ways for a function, or the derivative being a function itself, to go from positive to negative. That is, if in the middle, it becomes 0. And when the derivative is 0, we have a tangent line that has a slope of 0, a horizontal tangent line. Extreme values are points on the curve, if the function is differentiable through the curve, where the tangent line is horizontal. Then the one example that I gave of a function which is not differentiable is the absolute value function. The other way that a function like f prime of x can go from being positive to negative, or from being negative to being positive, is if it goes through a point where it is undefined, either a jump discontinuity or an asymptote. So we have here at the bottom of this absolute value function a point that definitely looks like a minimum. The derivative is undefined at that point. We don't really have a nice way of talking about the tangent line. In fact, there is no tangent line at that point. That's what it means for the derivative to be undefined, but still a minimum. So there's not quite a proof, but a little bit of evidence as to why the extreme values always occur at critical points. And that's why we named them as critical points. Definitions in mathematics are always invented, and they're invented by people who are trying to solve a problem and find a way to discuss something, and so found that giving that something a name would make it a little bit easier. So as an example, we might be asked to identify the absolute extrema of the function f of x equals 3x to the fourth minus 4x cubed on the interval, say from -1 to +2. Absolute extrema, as I said earlier in this video, must occur either at places where the derivative of the function is 0 or undefined, what we call the critical values, or on the endpoints. So the first thing we need to do here is identify the critical values. So we take the derivative of 3x to the fourth. Derivative of x to the fourth is 4x cubed. Multiply that by 3, we get 12x cubed. Derivative of 4x cubed. Derivative of x cubed is 3x squared. Multiply that by 4, we get 12x squared. Right? This is a polynomial function. Polynomial functions are never undefined, so we can just look at where this thing is equal to 0. And this one's not too bad to work with. You can immediately factor. There's a common factor of 12x squared, and when you factor that out, it leaves behind x minus 1. So by the zero product rule, either 12x squared is 0 or x minus 1 is 0. If 12x squared is 0, then x is 0. If x minus 1 is 0, then x is 1. So we have two critical values. Right? Critical values might be relative extrema, or they might not. Critical value doesn't tell us this is extrema. It tells us it might be extrema. But when it comes to identifying absolute extrema, knowing where to look is the bulk of the battle. So I'm going to now set up a table to check some values. And on this table, I'm going to check the endpoints and the critical values. We're looking at the interval from -1 to +2. So I'm going to check x equals -1, and I'm going to check x equals 2. We saw that this function had critical values of 0 and 1. In this case, both of the critical values were in the interval in question. If you have a critical value that is not in the interval where you are looking, you do not need to check at that point. But these are both in the interval where we're considering, so we do have to check them. Now we evaluate the function. F of -1 will be 3 times -1 to the fourth minus 4 times -1 cubed. -1 to the fourth is +1, -1 cubed is -1. So we have 3 minus -4, 3 plus 4, which is 7. Plug in 0. We get 0 plus 0, which is 0. Plug in +1, we get 3 minus 4, which is -1. Plug in 2. Let's see. 3 times 2 to the fourth power is 16. 3 times 16 is 48. 3 to the third power is 8. 4 times 8 is 32. And 48 minus 32 is 16. From here, very simply, we go back and look for the biggest and smallest. The smallest value occurs when x is 1, f of x is -1. The largest value, f of x is 16 when x is 2. And the absolute extrema must be those two values. Absolute extrema must always be critical values or endpoints. Right, so f of x has an absolute minimum of -1 at x equals 1 and an absolute maximum of 16 at x equals 2 when you look on the interval from -1 to +2. If we looked at a different interval, we'd probably find different relative extrema. If you look in the typed notes, you'll see another problem related to this where I give you some things that you're going to use a calculator and approximate values. I just want to point out that that's there. It's a thing that can happen if you need to grab a calculator and approximate values, especially when square roots show up in your function. There is nothing wrong with that. But I would like you to just dive in and take a look at the function g of x equals 2x cubed minus 5x squared on the interval from -2 to 2. Again, it's a closed interval, so you know that it will attain its relative or its absolute maximum and its absolute minimum. And I would like you to find those two values. Take a few minutes, see what you can do with this one, and I'll see you in the next video.